Earlier we discussed how multiple current loops could serve as a source of time-changing B fields that could induce an EMF and a current in a second set of multiple conducting loops. It happens that the time-changing B field can also induce an EMF in the very same set of multiple conducting loops. This process is known as self-inductance, or simply inductance, and it shows up in many practical electrical circuits, so it's good for us to discuss. To do so, let's look at the special case of multiple conducting loops in a solenoid that's part of a circuit. Let's assume that the solenoid has NS circular loops of radius RS, and the total length of the solenoid is LS. We'll assume that there is an EMF, say a battery in the circuit, and that initially the circuit is unconnected, so the current I in the circuit is 0. Now imagine we connect the circuit. I increases right after connection from 0 to something non-zero. In any real circuit, this takes some amount of time, so let's think about this time interval where the current is changing in time, increasing from 0. For a non-zero current, we know that there is a magnetic field inside the solenoid, and this is the magnitude of that magnetic field, as we discussed in an earlier lecture. The direction of the magnetic field is along the axis of the solenoid, and for this situation, the right-hand rule for currents in a wire tells us that the magnetic field inside the solenoid must point upward. Now there is a magnetic flux through each loop in the solenoid, and that works out to be just the product of B sub s times the area of a single loop of the solenoid, pi times r sub s squared, which works out to be this expression. Now since the current is changing in time, for some time interval right after connecting the circuit, that means the flux is changing in time. So there must be an EMF in the solenoid, that is, N sub s times the magnitude of the flux derivative of a single loop. And all that works out to be this expression. Now let's just rewrite that expression for the EMF of the solenoid here. The group of constants in front of the derivative of I with respect to time is called the inductance of the solenoid. The inductance is usually given the symbol capital L. So here's the EMF of the solenoid written more compactly. Let's now figure out the direction of the EMF. Note that as the current I increases, the B field in the solenoid increases upward. That means minus d sub s dt is downward. Using our right-hand rule for Faraday's law, that means the curly E field due to the time-changing flux in the solenoid must be as shown, counterclockwise as we view the solenoid as shown. Note that this is in the opposite direction of the electric field caused by the battery plus the surface charge gradients on the circuit. In effect, the solenoid's EMF is opposing the EMF of the battery for this particular situation. Let's represent this circuit more abstractly as so. Applying the loop rule here, we obtain the following expression, which, as we know, for the round-trip change in potential differences around the circuit must sum to 0. Let's summarize, starting with rewriting the loop rule here. Our representation of the solenoid is not completely conventional. Here's a better abstract drawing of our circuit, where the curly line is the standard symbol for the circuit element known as an inductor, with an inductance of capital L. Now here our inductor is a solenoid. However, there are other ways besides a solenoid to produce a circuit element that has a well-specified inductance capital L. So let's keep this in mind. One final point. Any real circuit with an inductor will have some amount of resistance. So we will need to consider that situation, and we'll do so in our next lecture on RL, resistor inductor circuits.